entries in that weight matrix. Then, so why we have done this? Because every layer don't have weights, like dropout layer don't have weights, only dense layer has weights. That's why in each layer this is checked that this layer has weight or not weight max. If it has weight, it will taken, and layer dot get weights will take out the weight matrix from that layer and get only the kernel weights, and 0 provided for the weights only. If we take 1, it will take the biases also. So we have taken only weights here, so W is here. So it is the weight matrix for each layer. We have in first layer for this loop, so this has taken the first layer weights, and then we will flatten the weights in a one-dimensional vector. So it is a numpy array now, and we will add it by dot append function in this list, which is weights. So for this loop, first layer weight has been added in weights list. For the second layer, this has been done, and the third layer again and again. For all layers, this will done for creating a weights list. So now we have a list which has multiple numpy arrays for each layer weights. So if there is a quantity in weights, this condition will do all weights equal to np dot concatenate, which will concatenate all weights arrays into a single array. So first we have multiple numpy arrays. Now we have a single numpy array which have all the weights of layers. So now the all weights is a single numpy array. Now we will plot the histogram of weight distribution. So what we have defined a figure window here, and by SNS library we call the histplot, which will plot the histogram plot, and all weights is a numpy array, and bins equal to 100 will create a 100 equal intervals for the entries of all weights, and KD equal to true will show a smooth line over the histogram, which I show you. And plt dot title dot prefix will be taken by the parameter which we have provided in this function. So title will be taken automatically. We don't have to provide again like zeros, ones, and weight initialization distribution, and again X label, Y label, the same things, and plt dot show. Else, if there is no entry in weights, it will print no trainable kernel weights found in the model. So again, we have distribute the MNIST data and normalize it, and model W zeros what will take the model training initialize a scheme which provides zeros, and what it will return? It will return the model which have weight matrix initialized as zeros. So it is a model W zeros, and again we will call second function plot weight distributions, which will take model and title prefix zeros. So this will plot the distribution function of the zeros initialization. This is a distribution plot. All weights are 0, and there is more than 2 lakh entries in weight matrices, and all are zeros here. So there is no diversity and learning in the neural network. And again, we will train the model with this with the extrain data, the model which are 0 weight initialization and validation data which have taken epochs 10 and batch size 128. So you can see there is no learning accuracy is very low and loss is very high because of the 0 initialization. And now we will see the once initialization in neural network. So all weight matrix will take the 1 entries only. So these things are same here. It will take the initialized scheme and return a model, and it will plot the weight distribution. So this is the same as previous, and the only change thing is initialize scheme as once, and here title prefix as once. So it will take the once initialization, and how the distribution will look like. The all entries has 1 and the frequency is high only for 1 entry, and the learning is very low, or there is nothing to learn. The accuracy is very low because all wet matrices are same, so there is no learning in the model, or no flow gradient flow because of the constant weight initialization. And now we will do the orthogonal initialization in neural network. Again, all things are same here. Just we will provide the orthogonal initial scheme here and see the distribution. So this is what KD equal to 2, this line, because of KD equal to 2, which I have told, the smooth line above the histogram plot. So here all entries are centered to 0 and high frequency for the near 0 entries, and low frequencies for the negative and positive near 0 entries. So for this, the accuracy is higher, and the learning is good for the network. You can see the accuracy is reaching up to 90. The change, and it will take the identity initialization, and this is how it will look like, the distribution. The 0 entries have high frequency, and the 0 to 1, it will moving ahead to 0 to 1, and it has very low frequency. But it has a good learning identity initialization other than the zeros and ones. And this is the random normal initialization in neural network. So we will provide random normal as a string in as initialized scheme. So it will take, this is how the random normal weight distribution will look like, centered at 0, but some sparse than the previous one. So it will take the entries of the weight matrix from like 0 minus 0.2 to plus 0.2. The learning is also good for this initialization. Now random uniform. So all things are same in every code. Just we have to change the string random uniform and see how the distribution will look like. So random uniform will take the uh, equally likely probabilities from the entries from minus 0.05 to 0.05. So this is the training using random uniform. And again, the Glorot normal initializer. This is the formula, if you have remember from the session, morning session. And this is how the Glorot normal weight initialization distribution will look like. This is this is also centered at 0. And Glorot uniform. Glorot uniform at high frequencies between here to here, and some low frequencies near minus 0.1 to 0.1. So now the he normal initialization in neural networks, which have standard deviation at this, and this is how the distribution will look like. So for the normal distribution, the entries are centered to 0, and the for uniform distribution, the entries are in a rectangular form. So there is equally likely probability for taking every entry, and in normal distribution, there is centered at 0. This is the difference between. So other than zeros and ones, all initializer are good. And it's depend on your task. You have to explore it by changing it every initialization scheme and check it will how it will behave on your data or on your task. So P uniform initializer here, that's how it will look like, the distribution. And Lacan uniform initializer, it will take the uniform distribution between this limit to this limit, the fan in the number of inputs here. And this is how it will look like. And again, the Lacan normal initializer, the formula is normal. It will take the normal distribution entries from 0 to 1 by number of inputs. So how this will look like. So these are all the initializers which you have learned in the then which initialization is performing best on your data. If you have any doubt in this code, you can ask. I hope I'm audible throughout the session.
Yes, yes, you were audible. Okay, so I think since there are no questions and the code also is already shared, am I audible?
Yes, madam. Yes.
Okay, so since there are no questions, we can go to other hands-on session on transformers. So I request Basan sir to kindly continue.
So my screen is visible, right?
Yes, sir.
And the code is visible, right?
Yes, sir.
Okay, so in this lab sessions, what we have planned is like we'll start with first creating the data set for like we'll use our own custom data for creating and developing the bird embeddings. For this, we'll use a masked language modeling method, which is basically from our own data. We will use masking in the sentences, and then we'll give input and output pairs to the BERT model to learn the embeddings. And then we'll also see that the embeddings which we could learn from our own data, how they perform on sentiment analysis task. Okay, and then as you know that BERT is basically the encoder based model based on the transformers. So in this session, we want you to explain that how we can use masked language modeling to learn the embeddings with the help of BERT model for our own data, and then the embeddings which we learn from scratch for our data, how they can be used for any downstream task. Okay, and then we'll also see some demonstration on long short-term memory for part-to-speech tagging problem, which we have discussed in the theory part. And then if the time remains, we'll also see some more demonstrations on related topics. Okay, so now let's start with this notebook. So first is we basically starting. We are first taking a data set based on the given from the Wikipedia, which is in English language, and then we'll see how BERT tokenizer is being used for tokenizing the for tokenizing the sentences, then we'll use masked language modeling, and for that we'll use different functions for doing the masking, because masking is very important. We have to decide that how much sentences should have masking in those sentences. So we have to decide, okay, 10% or 15% or 20% of the words from the sentences should be masked and all. Okay, so let's just start. First, I've just installed the dependencies and the packages which we'll use, and that is transformers, data sets, and Hugging Face Hub, and this is very common. And this is for just the parameters for reproducibility. Okay, so we start from this, where we first take the data set from Wikitext. Wikitext is a big corpus from which we are using Wikitext 2 raw version of it, from in which there are 4 versions, but we are using this version because this is a smaller version, and training a BERT model from scratch takes a lot of time. So for this notebook, I have just taken it like for demonstration purpose, but when you'll use for your problem, you can train it for longer, and you can use for your own complete data. Okay, so this from this data set, I have just taken 300 samples from the data, as mentioned, to just save the time for the for executing and running this model. But you can use this code for your data and your problem. Okay, so that you can easily update the data set settings. Okay, and then first we divide the data into 80% training data and 10% validation data and 10% testing data. So with this, firstly, we divide the training and testing data with 80% and 20. And then with this, out of 20% of the test data, it will split 10%, 50% of 20%. So that is like 10% of the whole data as a validation data and 10% as an testing data. Okay. So when we run this, we can see that trained data size is 240, and validation and testing data set is like 30. Okay. Now, this is uh, I want to show you that given the sentences or the documents to the like auto tokenizer for tokenizing, and then we'll see another method, which is data collector for language modeling. These two methods are very important for the pre-processing of the data. So what we are doing here is, in the first auto tokenizer, it is basically used for tokenizing the words and converting the raw text into the numbers that BERT can understand. We are using BERT-based uncased model that will understand the language, and it will do the tokenization. Okay, and this is data collector for language modeling is a function which we are using for given the sentences, it will do the masking. And there's a parameter MLM probability, which is given as 15%. So what it will do is it will like collect the data, and it will mask 15% of the words as mask. Okay, and then the model will have to predict the masked words, and based on that input and output pair, so BERT model will be learned. Okay, and now what this is doing, I'm trying to show you how this tokenizer is working on this sample data set, sample sentence, which is like transformers make natural language understanding a breeze. Okay, and then I just print here. Okay, so the tokenizer is so we have just created the objects of the tokenizer and data collector for language modeling. Now we just give the parameters to them. Tokenizer is first taking the text as a tokenization token as a parameter. Sorry, truncation is true. It means we have set the maximum length of the input as 16. So what it'll do is if the length of the sentence is more than 16, so then in that case, it will truncate the extra words. And if it is less than 16, so it will do the padding. So maximum length, obviously, you can also set according to the maximum sentence length in your data. So accordingly, like for this parameter truncation is equals to true, it means that if the sentence is more than the maximum length, it will truncate the words, and if it is less, then it will automatically do the padding. Okay. And then we just convert the token the words which we has been tokenized into the tokens, and we give the IDs to them. Okay, so which as you know, we are already doing that. We have to give the IDs to each of the tokens so that it can be fed into the network. And this is for like the collector which we have defined over here, data collector for language modeling. So it will just take all the sentences and it will do the masking, actual masking, which we already discussed, that 15% is the parameter which we are passing. So it will automatically like pick up the words and it will do the masking. Okay. And then again, we are just converting the sentences after the that masking. Okay. So let's see here what we are getting for this sentence. Transformers make natural language understanding a breeze. Okay. So first is like tokenize IDs. So it starts with the first token. So first token is the CLS in BERT. If you remember theory also, the first token is always a CLS token, and separator is a special token, which indicates that it is the ending of the sentence. And apart from that, all these are the padding, because we have fixed the length of the sentence to be 16. So each of these IDs basically represent the index of the particular word in the vocab size. So vocab, it means like transformers is on the position of this in the vocab size. So accordingly, they are like having the IDs. And after doing the masking, you can see the tokens are this, and this is the padding, and these are the labels. I don't know why we could not just okay. So this is just IDs. We have not called the actual function for data collector, and we have not basically printed after that, because this is mask tokens and label tokens. So third is tokenization and the collector, which we already discussed. This is just for showing you another example for it, but I could not run this now because it takes a lot of time, and this notebook is disconnected. But you already have this notebook with you all, so you just run in your system and you will be able to see the masking also. I don't know if I have printed below somewhere. No. So when you will run this, you will see the words after the masking also. But here I have not printed that part. But anyway, you can try that. So this is another same function, but just I thought like I would show you on some more example sentences. So now you see that we can use data collector for language modeling method for doing the masking, and we can use the BERT tokenizer also. So we just take the token sentences, tokenize them, and use that function for masking in the sentences, and that prepare for the data for training the BERT model. Okay. Now we define BERT model. So originally, the BERT base model has 12 layers with 768 hidden size and 12 heads. But for this, we just creating this model for 2 layers of the transformers, and we have 128 hidden size and 2 heads. Okay, just for saving the computation time. But you just have to change this to the required size, whatever you want. Okay. So hidden, these are the parameters which we have to give for the BERT model, which we want to train for from scratch for our data, and the data which we have just prepared. So this is the configuration for all the related to model. Okay, so this is like how many hidden size we need in our BERT model, how many hidden layers we need, how many attention layers we need, how many intermediate layers we need. We can just set all these parameters, and then we can just directly use this auto model for mask language model that will instantiate from scratch for training the model. Okay, so with this sorry, with this we can update and change our network also. Now we have defined our model, BERT model, with different parameters which we want to use. So when you will train the model, you can just change the parameters and then see, or you can also like create the same parameters which is like original BERT has, and you can also use different architectures. Okay, and this is parameters for the training part, which we generally use for training the model, like when we compile the model. Okay, so these are the parameters. Let's see them. Like first is output directory, which will save all the checkpoints and the data on the drive. And then we just see that when the number of epochs, that what is the validation set at after end of this. And we have save the model at maximum 2 times, it will only save 2 best results of the checkpoints. It will not save all the checkpoints after each epoch, but just to save the space on the drive, we can just set I just need to store only best 2 models, and then learning rate and weight decay and all these parameters we can set to set for the training of the model. Okay, and after setting the parameters for the model, and then for the training part. Okay, so the first we have to define the model, what are the parameters, how many layers and all we should need. And then we also set the training parameters, like what kind of parameters we required while training. Okay, number of epochs, learning rate, and all these things we can check. And now we actually create the trainer function. So in which we just pass the model name and then arguments of the model, and collector, data collector, which hides 15% of the data here, which we have defined earlier, and the tokenizer, the data for the training and the validation. Okay, so all this is actually given to the model. It's very similar to the fit function which we use in other implementations, and we just start this training part. Okay, so this part will take a lot of time based on your computational resources, and also based on the parameters which we have defined. For this, it took uh, three epochs we have just run, and validation loss was decreasing, but very slowly. But we have to just to save the time for the computations, for execution, we stopped it here just to we wanted to explain the code and the concepts of this. So for your problem, you can easily run this. Okay. Now, this is an example which you can just run on your system. That's just to show you how or what we have learned from our models. Okay. So for this is just creating a pipeline in which we give the model and tokenizer to the model. to the pipeline function, and we set these three examples and give the masking, and then want to see if how this BERT model is working, and we can just run this code, and then given this sentence, it is now producing five best possible words which should be placed at mask based on the training of the BERT model. But since we have not done very good proper training of the model, but you can see that the words are predicted based on their probability. So once you will have very good training of the model, these will start giving better outcomes. But this is the code where you can see what is the word which is being predicted by the BERT model. Okay, so like Albert Einstein published his theory of next word is masked in 1905, and that word predictor is the okay. Now we can once we give this unlabeled data, we can create mask language modeling for creating the input or output samples, and then we have a big network encoder based network transformer encoder based model in which we can like train using the data which we have prepared. If we'll have sufficient and large number of data, large amount of the data, so the model will learn very good representation of the words and the sentences. Okay, and then we can use those word embeddings which we have learned from data set, which is like Wikitext data set. Now we'll see that how we can use the embeddings which we have trained for that data. Now we'll preload those embeddings, and we'll use those embeddings for sentiment analysis problem. Okay, so so auto model for sequence classification is a function which I'm just directly using it to just show you how we can do the sentiment analysis on the word embeddings which we are getting from the previous model. Okay, and for this we just define the network, okay, model, and you can see it is taking the configuration from the BERT model, and you can see the network. In the first layer, we have embedding layer, in which we have the vocab size to be 30,522. 128 is your like dimension of the embeddings, and then we have two BERT encoders. Okay, two BERT encoders, and then we have dropout layer, and we have that intermediate layer with 512 for fully connected layer, and we have pooling layer, and then finally we have a linear classification with two as a like output classes. Okay, so given this network, you can also use these embeddings which you have just learned for any other for other classification also. But this is a standard, like very simple classifier, which is basically taking the BERT embeddings as an input, and then we are doing the classification with linear model in the end last layer. Okay, you can see this network architecture. Now we are taking another data set, which is AG news data set for binary sentiment analysis problem, in which we have generally this data is having 4 classes, but we are just converting it to binary classification problem to show you how this model can work. Okay, and then we just do the splitting of the training data into same 80% training and 10% validation and 10% testing data, and then we are printing the data sites. So now for this data, we are taking 800 training samples for the labeled samples, and now validation sample is 100, test samples is 100, and then we create this evaluate function. Okay, so that will metric will be used for measuring the accuracy, which we have taken as accuracy. Okay, and as similar to what we have used earlier. Now we first set all the training arguments of the model, and then the training parameters. So this is the parameters related to the training. Okay, so model is already defined. Sorry, so model is already defined. So we have to just define the parameters and configurations for the training part. So how many epochs and like batch size and all. Okay, and then we just give all the parameters and the models to the trainer function. So it will take all the data from the training and will use validation data for training of this model. Okay. And then we are using a trainer function which will actually train this and call this object, and then it will run. Okay, so then this is evaluate function which will print the performance of this model. And for this training, for this problem, we are getting 66% of accuracy, which is obviously very low, just because we are not doing complete training for this model, because to train the BERT model from scratch takes a lot of time and computational resources. But obviously, if you have GPU, or if you have some real data for your problem, from your research problem, so you can maybe you can run the model for your complete data. Maybe it will take some time, but obviously you will get very good results as compared to other methods for embeddings like Word2Vec and or maybe like very competitive to the CNN or RNN methods for sentiment analysis. But obviously it depends on what is the architecture and data you are using for training. But yes, so this is a very important and popular model for creating the embeddings and for using in NLP downstream task. This is one of the most important model, which nowadays becomes like researchers are basically doing different variants of this and using for their problem. Okay, so if you have any questions on this notebook, which we have already shared with you, please see to that and let me know if you have any doubts. Okay, so I think now we'll also demonstrate other problem, like part of speech detection using the LSTM model. And Pooja will share. Request Pooja to please share and
Yes, sir.
yes.
Uh, Sir, is the screen visible?
Yes, yes. Okay, so first we are
Okay.
showing this one. Okay, oh, or whatever. So Pooja, first, okay, we are taking LSD.
Okay. No, sir, we can start with Word also.
Okay, I think BERT will be better, because we have already just seen how we can create BERT from scratch and then use it for sentiment analysis. Now we can see how different variants of BERT can be used for question answering, and then we'll can complete the remaining. Okay, Pooja, so I think you can continue with this script.
Okay, okay. Okay, so welcome back, participants. Here is in another application of BERT model, or more precisely, I should say the transformer structure, the attention mechanism that that will show you the strength of attention mechanism, that how strongly it captures the semantic meaning of the sentences or the data that is given to it. So let us start with the famous uh, task that is handled by BERT-based models. So in this notebook, we consider a very famous data set, that is squared data set, squared 2.0 data set. This is the modified version of squared data set, which consists of answerable as well as unanswerable question given a context. So in this notebook, we will deal with basically 4 variant of BERT model. First one is Roberta, second one is BERT-based, Distill BERT, and Albert. So let us start with the coding part. So first, we start by importing all the necessary libraries that we will require during the coding part. So we start import JSON. We import JSON just because our data set is in the format of .json file. So that's why we import this library. Import random just to choose the random sample from the data set for the processing. Import torch, numpy. As we are dealing with BERT model, so we import transformer. From there, we import Roberta tokenizer, Roberta for question answering. For the embedding of, as we are dealing with the sentences, like questions are in the form of sentences. So from the transformer library, we import sentence transformer, import sentence transformer module from there. So first start with the data set, like how the data set look like, how much entry the data set is containing. So first we will print how the data set look like, how much entry it is containing. So this is for the training data set. As squared V2 data set is already splitted, so there is no need to split the data set manually in the training and the testing part. As you can see, I have uploaded 2 files here. One is train V2.2, that is the training dataset. The another one is Dave V2.0.json, that is the validation or testing dataset. So in this code, what we load our training dataset. And after loading the training dataset, as I have already told you that the dataset is containing context, the question based on the context, and the answers, if the answers are extracted from the context, given context, or otherwise the answer is given as blank, that is the unanswerable question. So we start by defining our context in the training data set as train context, the question in the training data set as train questions, and likewise the answers. So for counting the data set, we start with the data. As the data is in the format of data, then with paragraphs, in the paragraph, the quantity paragraph in the data shows the context. The QAS tag in the data is for the questions, and the answer tag is in the data file is for the answers. So we count the train context, then questions, then answer, and this is how we print the data set. So in the training data set, we have in total of 19,035 context, and we have 1,30,319 questions from based on these given 19,035 context. So similarly, we print the size of our test data set. So here we load our test data file. We select answer count with 0, context count, and iteratively we add 1 to each until the data set finish. So this is how the output of our testing data look like. The test data will contain 12,004 context, 1204 context in total, and a total of 11,873 questions from these context. So now after counting the context and the questions from both the training and testing data set, we will come to the part that how the data looks like. So by here we load our training file, and from training file we choose any random data that is in the data set. It is tagged by paragraph, so we ask for paragraph, and we choose any two samples. The random sample in the training paragraph is 2, and we print that chosen random samples just to show how the training data look like. So this is how the training data look like. Sorry, again it printed the output. No. Yeah. From here, we choose 2 random sample from the training data, and this is how the training sample look like. And we print our training sample, context, question, and the corresponding correct answer. Similarly, we load our test file. We chose any 2 random sample from our test file, and we print the output, the context as the context to the question as the question tag, and the correct answer is this. And we print all these things from the test data also. So this is how our training sample, first training sample, this is the context that according to the United States Census Bureau, the city has a total area of 656 square miles. This is a given context, and based on this given context, what is the square mile area of person? So this is the question, and if the question has information, if the question is answerable from the data set, so this question is answerable, and the correct answer in the data set for this question is given as 565 square miles. So similarly, this is another context from the training data, that the new piece would only last for 2 years, was recommended in the aftermath of John's decision. This is the second context, the corresponding question, and the answer. The samples from the test data looks like this is a given context, this is a corresponding chosen question, and this is the answer for this particular question. Likewise, the sample 2 of the test data. So after evaluating the size of the training in the test data, and after seeing that how the test data and train data look like, we start by processing the data. So as the data consists of sentences, so first we should go for the embedding of the questions, the context, and the given answer to provide our model. So here we use the sentence transformer model, that is in particular OL mini LM L6V2, just in order to compute the embeddings. So start with the coding part. Here we import our required libraries, JSON, random, torch. From the transformer, we directly import the models, Roberta tokenizer, Roberta for question answering. So one additional thing that we need to consider here is, here we are skipping the training part, as training BERT-based models, BERT variant or transformers-based model is computationally too heavy. On our system, it is not compatible to train these models, so we just use pre-trained model in order to do the processing of question answering in this code. So here we directly import these 4 models, the Roberta tokenizer, Roberta for question answering, BERT tokenizer, BERT for question answering, DistilBERT, the Albert tokenizer. These are the 4 considered tokenizer and their corresponding model that are already pre-trained for question answering task. So we imported these 4 models. From sentence transformer, we import sentence transformer. So now starting with the test data, because there is no requirement of train. List has the paragraph. In paragraph, we find the data, paragraph, then question, and the corresponding answer. So we randomly choose one paragraph, that is one context, and one question based on the selected context. So this is how we chose a context and the question. The question is chosen randomly from the already chosen context and the corresponding answer. So we print the selected context, the question, and the correct answer corresponding to the question. after loading and after choosing the context and the question, now we start it by feeding to the model. So just in order to get the embeddings of the chosen sentences, we load our sentence transformer model, that is all mini LM2. So if the actually I have already told you that the data set consists of both type of question, the answerable question as well as the unanswerable question. So there is a if else loop. The question is only processed if the question is answerable. That if the correct answer is not found in the sample, we skip this question and try to choose another random sample from the test data. So this is so that's why we use if else loop. If this condition is violated, then we start by choosing another question from the test data. So if the true answer is the correct answer in the data set, we start the embedding of the answer by using the SBERT model. We have already defined all our model as Roberta, the Roberta tokenizer from the library. Roberta model. Similarly, we load our BERT model and tokenizer for DistilBERT. We also load both the model and tokenizer, and likewise for Albert. So now, in order to calculate, like we have already discussed about evaluation metrics, we all know. So in case of sentences, how do we calculate it? We calculate it using cosine similarity. That how do we evaluate whether our model is predicting the answer correctly or not? So what we do is, as a model is providing us the embedding, so we can easily calculate cosine similarity. So for the evaluation part, we calculate cosine similarity between the ground truth that is in the data set and the predicted answer by the model. So we load all our tokenizers and all our model and set the model to the evaluation mode. Now, what we did is we start assigning the model IDs. This is all we discussed in our skip gram and SIBO part also, that how we assign indexes to each word in the vocabulary. We predicted the answer. We also tokenize the predicted answer by the model. The predicted answer is decoded by the tokenizer, the predicted embedding. So here we are just whatever the model is predicting, we are decoding it again in the understandable language or in the alphabetic form. As the model is predicting the embedding for answer, so we are decoding here it using the decode function just to understand it what the model is actually predicting. So this is how we print all the four things, which as we have already chosen a random sample from the test data. So the selected question is mention says that composition with prime number was inspired by what? So this is the context. The prime numbers have influenced many artists and writer, the French composer, this and this. This is the provided context, and the correct answer for this chosen question is the moment of natures. So what let's see what our chosen BERT variant have predicted. So this is the answer for the Roberta model. Roberta model has predicted the answer is moment of natures. So you can already see the correct answer in the ground truth is the moment of nature. So just because of the absence of the article, the cosine similarity is coming between the predicted answer and the ground truth is coming to be 9.7. As the BERT base is predicting DistilBERT is also predicting the answer which is matching to the ground truth, but with some additional information. So this degrades the value of the cosine similarity, and model Albert is not giving any answer at all for this question. So the cosine similarity for this blank prediction and the ground truth to be 0.1 only, which is close to 0. So this is how we can evaluate, and we can see that our pre-trained BERT model are predicting answers very good. Now, this is the application for the question answering. Now, to see the strength of transformer architecture, what we did is we said some of the neurons or some of the weights of these models, as these models are we set a fraction of these parameters to 0. That is what we call as dropout. So it is the fraction of these of parameters, and we try to fit whatever. So zero. So intense but just in order to get the embedding. So variants for the setup, we use the same of neuron to 0 while predicting output for a given input from the test data. So this is the code for this particular thing. Similarly, we import all the necessary libraries. We activated all our tokenizers and their corresponding model version. We load the test data. We visualize our data list by paragraph, then data, then question. Then we select a random choice of context. From the selected context, we select a random question. And what we did is we activate, here we have printed all the selected question, context, and the correct answer corresponding to the question. We load our SBERT model to get the embeddings of the provided sentences. Here we again executed the if statement. If the correct answer is not found, then we exit the loop and again start by looking by choosing another random question. If the correct answer is available in the data set, then we go ahead with the coding part. So here we have loaded all our tokenizers and models. Now, what we did is in this particular part, we enable dropout. We chose a dropout rate of 0.1%, that is 10%. What we did is we put 10% of the weights or say neurons of the model to 0 during the inference part. You can change it to any number, but on increasing the value of the dropout, say you increase it to 30 or 40%, the model starts losing its information, whatever the model has learned from the training. So on putting a fraction of say 40% or 50% of neurons to 0, the half of the information is approximately lost by the model. So we just chose it to be 10%, that on putting 10% of neurons, what happens to the model. So now we set all our models to the evaluation mode, and we initiate all our tokenizer and models. We start our tokenizing our input, and this is how we start the list, the predicted answer list, and the cosine similarity corresponding. So in this case, how the output look like is here we print all our model to the corresponding sample and the cosine similarity. So this is how the output look like. We select a context, that is Fresno is marked by a semi-arid climate. This is the context that is selected by the model. This is the selected question, that how much rain per year does Fresno get on average. So the correct answer in the data set is around 11.5 inches. So after setting a fraction of neurons to 0, that is 10% we have chosen in this code, the output given by all the models is correct. So this shows the power of attention mechanism, that after setting or after deactivating a fraction of neuron, the model is still able to predict the things correctly, which shows that how strongly the model captures the information while training. So here you can see Roberta is providing the answer is 11.5 inches. That is showing a cosine similarity of 9.2. As in the data, the answer is around 12.5 inches. So just the model missed the word around, the cosine similarity comes to be 9.5. But in the semantic meaning, the answer is correct. The answer is totally correct. Similarly, BERT model is showing an answer of 11.5 inches. Distilbert is also showing the answer to be 11.5 inches. And here also Albert lacks to answer that maybe just because of Albert is a light version of BERT, maybe just because of its learning capabilities, Albert is not able to answer the question. But this is how all the rest of the three models are performing after activating the after deactivating a fraction of neurons in all the respective models, the model are still able to perform superiorly. So there is another what should I say, another application in which we can see the strength of attention mechanism. Now, in this part, what we have done is, as we have already a question in the data set, so we have paraphrased that question. Just by changing some words with their synonyms, we have paraphrased that questions. So instead, just to check whether the model is capturing the semantic meaning, because the meaning remains the same, there is a part, we are just only changing it to lexical structure, not the semantic structure, as the semantic structure remains same. So how the model performs. So in this part, we have used a paraphrase pipeline, that is text to text generation pipeline. And this is the model that we are using, the BART based paraphrase model we are using to paraphrasing our question. So here we have already we are loading our test data. We are choosing a question from the test data. If the answer is there in the test data, we are choosing that question. Otherwise, we skip to the next question. We are checking the availability of the device. Now we load our question answering pipeline, that is QA pipeline. For we have loaded all our tokenizers and the models, pre-trained models from the question answering. The model in this case, we use a Roberta Distilbert. So there is another problem that we after paraphrasing, we have to check whether the meaning of the paraphrased question and the original question is still same, or does the paraphrasing change the meaning. So for this, what we did is we calculate a cosine similarity. This is the original embedding for the question, that the original question, and the paraphrased embedding for the paraphrased question. And what we did we calculate cosine similarity between the original question and the paraphrased question, the original embedding of the question and the paraphrased embedding of the question, just to ensure that to how much extent the paraphrase model changed the original question. So for this purpose, here in this purpose, we took our threshold as 0.75 to 0.98. That the 98 shows that the model at least go under some kind of paraphrasing. As the cosine similarity 1 shows that the paraphrased question and the original question is to be same. So we don't want that scenario. So we choose our upper bound to be 0.98 and the lower bound to be 0.75, just because we don't want to lose the semantic meaning of the paraphrase question. So here we print all the original question, the paraphrase question, and the cosine similarity between the original question and the paraphrase question, and the correct, if the cosine similarity falls in our defined threshold range, then only this process is executed. and the correct answer is also predicted. So now here we run all our model pipeline, the question answering pipeline. The original answer, this is the paraphrased answer. The original answer is the model. The correct answer is the ground truth that is provided in the data set. And the original answer is that answer which is provided by the model for the original question. And the another answer is the paraphrased answer that is provided by the model for the paraphrased version of the question. So please don't see terms. The answer is the by the model for the original and the paraphrased answer respectively. So after predicting this ones by the model, the causality between the like here, what we did is we did embedding of paraphrased answer, we did embedding of correct answer using the S-BERT model, and then we calculate the cosine similarity. The cos-sim, this function is calculating the cosine similarity between the paraphrased answer embedding and the correct answer embedding, just to check whether these answers are closely related or not, and we print all the required things. So this is how the output look like. Let me show you. You can see this is the original question, that what do some believe in the Treaty of Versailles assisted in? And this is the paraphrased version. What is the importance of the Treaty of Versailles? So between, as we can see, the cosine similarity between the paraphrased question and the original question is 0.81. That falls in our threshold. And we can also see that the semantic meaning of these two questions are almost same. So the correct answer that is given in the test data for this question is Adolf Hitler's rise to power. Now, what our answer is predicted, the original answer, that is the answer predicted by the model for the original question is the Adolf Hitler's rise to power, and the answer predicted by the model Roberta for the paraphrased answer is same, helping Adolf Hitler rise to power. And the cosine similarity between these two answers is coming to be 0.87. That is close to show that the differences or the answer by the model is same. It is still, but in this case of
Hello?
it is not.
Hello?
It is not. Yes, ma'am. Yes, ma'am.
Yeah, your
Hello,
voice
ma'am.
is cracking, actually. Hello? Am I audible?
Yes, ma'am, yes.
Yeah, so Buja,
Ma'am, now, hello.
no, your
Yes,
voice
ma'am,
is cracking, actually. No. It's cracking. So I suggest that because we are already past time, it's already 5 p.m. So we can conclude with this notebook. You can share the BERT
Yes,
variants
ma'am.
and
This is,
LSTM, both the notebooks with the participants on the Canvas portal, and
yes, ma'am.
conclude this session.
Okay, ma'am. So we are done with this part. Just this is the last of the output. I am explaining the output shown by the model. So just in 1 minute, we can conclude with this notebook.
Okay.
I will share the LSTM notebook with the participants. They can try it on
Yes.
their own.
Yes.
So this is how the models are behaving corresponding to the original question and corresponding to the paraphrased question. Here also we can see Roberta is predicting almost correct answer for the original question as well as the paraphrased version for the question. Distilbert lacks to predict the answer for the paraphrased part, and Albert here is predicting answer correctly. Similarly, Bert Base is also predicting answer correctly for both the cases, for original question as well as for the paraphrase question. So this shows us the power of attention mechanism or the transformers based model, that how strongly they capture the meaning, that on paraphrasing also they are able to predict the answer correctly. So instead of learning the lexical structure or saying the as it is what's the question in the data set, the model learns the meaning of the question or the given context. So this is the attention mechanism of these models. These models are actually very good. They capture the meaning very well. So these two applications, the one is paraphrasing and the another one is enabling dropout during the prediction part, shows you the strength on the say ability of capturing the meaning of transformer based model. So this is how this is all about question answering task dealing using BERT variants. So is there any doubt from the participant side regarding this coding part or anything else in this notebook?
Okay.
Hello, am I audible?
Yes,
Yes, yes,
you are audible. You are audible.
There is no question, so we can conclude.
Sorry?
I'm saying if there is no question, so we can conclude.
Okay.
Please.
Okay, so thank you, Pooja, and thank you, sir, for this session. I would like to thank Dr. Basant Agarwal for his continuous support and all his knowledge and his lectures that he has shared with us over the past 5 days. I'm really, really grateful to him for accepting our invite and be kind enough to support us in a major way. Thank you so much, sir. Your efforts mean a lot to us.
Thank you, madam. Thank you for inviting me. Thank you.
Yes, sir. So, participants, with this, we come to the end of this course. After this session, there is only quiz. There is a quiz that will be published on the Canvas portal. You have already taken quiz 1. This is the quiz 2 for this entire course. The second quiz will be published at 5 p.m. now, I mean, around in 5 minutes or so. And it consists of 40 questions. You will be given 40-minute slot for attempting the questions. And the quiz is open till 11:59 p.m. today. You can take any slot in between this time and attempt the quiz. So as you all know that 40% marks are required to earn a certificate, and you need to attempt both the quizzes. In any case that you have not attempted quiz 1, we cannot reopen it now, but I advise you to please take up this quiz 2, because this is evaluation on the entire course. Quiz 1 was just the evaluation on first 2 days. So quiz 2 is very important in the amongst these two quizzes. So those who have not attempted quiz 1, please attempt quiz 2. Okay. And if anybody has any other doubt, I hope I was audible.
Yes, ma'am.
Yes, ma'am, you are audible.
Okay.
Any
So,
feedback or anything if any participant wants to say?
any feedback, if anybody wants to give, they can speak on the chat box, or they can write to us on email also. So we began this course by exploring the geometry of loss surfaces and some foundational challenges in optimization. And then we saw some activation functions, gradient descent variants, and also nuances of learning rate schedulers. So these sessions basically gave us a groundwork for understanding the optimization procedure. Then midway, we we moved on to more advanced and practical topics, including model compression, transfer learning, and overfitting. Okay, so this shed a lot of light on trade-offs and choices that arise while you are optimizing a deep learning model for real world performance. The key highlight of this course was that it was kind of a blend of cutting edge research and industry relevance, from language modeling and embeddings to transformers and hyperparameter tuning and deployment challenges in healthcare and other domains. So I'm really, really thankful to all the expert speakers that have contributed to this course and added immense value, showcasing the evolving landscape of deep learning and optimization, both in academia as well as in industry. Let us carry this forward with some critical or not so critical feedback if you have, and may this journey continue as we connect to more collaborators and more students. So any other thoughts on this are welcome. And I believe the quiz is published now, so let us know if you are able to access the quiz. Please take up the quiz. Again, I repeat the information on quiz. You will get 40 minutes. Once you start with the quiz, you have to finish it in 40 minutes. And you can attempt the quiz till 11:59 p.m. in the night today. Please make sure that you attempt the quiz. We will not be able to open it again in any circumstances. So please take up the quiz again. This quiz now. Any doubt, any feedback that you wish to give are welcome. So certificates will be available soon after the quiz, maybe in next week. Okay, so if there are no questions, then we can just conclude this entire online program on the optimization for deep neural networks. All the very best. And in case of any doubt, there is this WhatsApp group. You can